I'm going to stand down here if that's okay. And I'm the head of IT, CIO with Ciner Resources, so I'll tell you a little bit about ourselves. And really just wanted to talk about our journey into IoT and into the smart plant. And so we're fairly new on that journey, but we've made a lot of progress quickly. So we're fairly new, made a lot of progress quickly. So in the last couple of days, I've talked to a number of folks here. I've sat in on presentations. A lot of people, a lot of companies here who've done some very neat things and are further along than us. But if you're just getting started in machine learning and decision science, we wanted to share a story of how we've made traction and moved very quickly and give you some hope that you can move on here as well. So let's start the journey. If we can move on, I'm going to give you a preview. There we go. So what is Ciner, Wyoming? And first of all, it's pronounced Ciner. Ciner. How does that happen? How do you get that out of C-I-N-E-R? We're owned by a Turkish parent company, Ciner Group, and the C in Turkey is pronounced like RJ. So Ciner, Wyoming is a natural soda ash producer based in the Green River basin of Wyoming, southwest Wyoming. Very beautiful part of the country, very arid. So we refine soda ash from a natural feedstock of sodium sesquicarbonate, which is trona ore. So I'll use the trona ore. So it was developed in this basin. There was a lake, go shoot there. There was some volcanic activity that put a lot of sodium in the area. There was some natural carbon decay, and over time the lake evaporated, and so the largest basin of trona in the world is right here in Green River, Wisconsin. And so us and 3 of our competitors produce about 20% of the world's soda ash production based out of Green River. So it's mined in the mine, it's calcined, so we liquefy it, we remove impurities, we convert it to Na2CO3, which is soda ash, and that's put on rail cars and we ship it around the world. And as far as uses of it, about half of it goes into glass, chemicals, soaps and detergents, so bacon, Arm & Hammer, things of that nature. So that's how it's used. So let me tell you a little more about our journey. So we started last spring, really, and Jolene's our smart plant lead, and she was using some OSIsoft plant intelligence and starting to get some interest in the company of what we could do with this historical data. And we decided that we learned a lot. I guess my first expectation was we could use this data to predict maintenance on our equipment and try to reduce unplanned downtime. And that's certainly a value, but as we looked at it, we saw lots of other areas that we could drive value from the smart plant, including process optimization. Being at a mine, safety is a major concern, so mapping safety data onto our plant to provide visibility of that information, environmental data collection, quality. There was lots of different things, dashboards and executive dashboards. So we came up with 5 areas last spring that we wanted to prove out that we could deliver value. And over the course of a couple months, started demonstrating that there was value here, and it was theoretical value at that point. So we come into last fall, about October timeframe, and we said we want to get deeper into both the process optimization and the predictive maintenance, and we need to bring in some partners to help us with decision science and machine learning. So we placed 2 small bets on those. One was with partners with Microsoft and OSIsoft and a third-party data scientist company, and we were going to pair them with a group in our company, a continuous improvement group that was doing a design of experiments on one particular part of our plant, and figure out, with data, could we learn more about that process than we were doing just with our design of experiments, which is taking a lot of time and a lot of effort. The second bet was with the company Falconry, and Jolene's going to talk about that more in detail, using that decision science built into the software where we could tie our operators more tightly to the pattern recognition and the decision science, and we got to a much faster result with that one. So let me give you a bit of the problem overview. So we mine trona about 850 to 900 feet below the ground. We have these continuous miners electric powered vehicles down in the mine that are constantly chewing up the trona ore, putting that on belts, sending it miles underground, up a hoist, and then we start it down a refining process. One of the challenges is with ore grade. So as we're mining different parts of the seam, there's different ore grades and different insolubles, different shale, different rock, different components. So we measure bad ore as anything 83% or below. So that 83%, 85%, 90% is the pure trona capacity, and the rest of that is insolubles. It could be water, it could be impurities, it could be shale, something else. Well, we do have a lab that analyzes it, and they do it twice a day, but we get the results the next day. So the problem is our operators are blind, and if I take a step back to last April, we did a maintenance and we changed out the filters at the beginning of this process. And before we changed that, we actually had some visibility to the opacity or the ore grade changes as it came into the process. We changed out that filter, and all of a sudden that visibility, that signal for our operators to know bad ore is coming in, went away. And so the last few months we've been struggling with, and more unplanned downtime, because this particular piece of equipment, this Vertimill, was plugging up with insolubles and we had no visibility. So we started looking at, oops, let me go back here. We started looking at how can we give visibility to the operators on what impurities are coming, on the changes in ore grade, on what types of insolubles are in there, because it may be a certain ore grade, but the insolubles are harder and they take longer time to chew up, or they're a softer type of rock and they chew up much faster. So we needed to give visibility of the ore grade to the operators real time so they can make decisions on that. The Vertimill then can be overloaded if the insoluble is too high, if the PSD, the particle size distribution, is too big, and these 2-inch metal balls that grind up that insoluble get spaced too far apart. They can't do the grinding that they need. Or inadequate loading. We go through a 5-gallon bucket a month of these metal media balls, and so right now unless we've stopped the plant and are looking in there, there's no visibility to how many are in there. So we needed to give visibility to the operators of when is it time to reload and make sure they don't overload with too much media. But the key problem, and as I talk about our journey and hand over to Jolene, is really driving with a vision of where we want to go, with identifying a business value that we're trying to achieve, and then by making small bets and learning and then going into operationalizing that. But this particular problem, when this Vertimill is down, 60% of our production rate is lost. And that can be lost for 4 to 24 hours, depending on how bad the upset condition is and how much recovery time we need. So the other part of our plant that produces 40%, it was designed to handle a lower ore grade capacity, has no issues with ore grade changes. This particular Vertimill was designed for a 90% ore grade. So if we slipped into the high 80% ore grade, we started seeing problems. To go replace this piece of equipment, minimum 1.5 to 2 years away, significant capital investment. So we may go down that path, but what we're trying to do now with machine learning and with data and analytics is let's solve it. Let's make sure we can flow the optimal rate of production through this system using the existing equipment we have. So I'm going to hand it over to Jolene to talk through the details of the process and the machine learning that we did.
So I hope you can all hear me, correct? All right. I apologize in advance. I love to talk about this subject. It's absolutely my favorite thing to talk about. But my thoughts are everywhere, and so I can be really scattered. So I have notes, and I may pause a lot. Anyway, so I'm the smart plant lead over at Ciner, and I started playing with the PI system about 3 years ago, so OSIsoft archived data, and looked at a lot of trends and a lot of signals, and was really interested in this predictive type of, condition-based maintenance, predictive analytics. And you can struggle with that, and you can really burn your eyes out on trends and what you're trying to find in simple analytics. But first I want to tell you a little bit about our process, and then I'll get into our pattern recognition. So this is our process. We mine the ore, we take it to an ore bin, we then convey it over to a calciner, and calciner is actually where we heat it up and we turn it into soda ash at this point. We then take that product from the calciner and we go ahead and put it into the dissolvers, where we make a kind of a saturated liquor that's actually our final product in liquid form. From there, we have to remove the impurities and insolubles, so we just do a simple solids-liquid separation. And those solids are mechanically conveyed using this spiral classifier over to the Vertimill. Once they get into the Vertimill, they have to be ground. We ground this product so we can actually retain any or discover any trapped soda ash inside the insolubles. The Vertimill, if it's able to grind, if the balls are able to contact each other, then the balls will move up the center of it, grind the material, come around the sides, and fill the voids in the center, and you've got this circular motion. If the balls are unable to contact each other, and it kind of turns like fruit in Jell-O, it technically will just kind of screw the screw conveyor will take all that material up and just spit it out the top. So it's not a fun thing to clean up, as you might imagine. So to tackle this problem, if I can get this to work, what we decided to do is, talk to the operators, and we wanted to see what they were looking at. So, so we wanted to identify what they were looking at and what they would use for overload conditions. And they were actually looking at things, they were identifying signals that were happening directly on or around the Vertimill. So they essentially didn't have a warning, they just reacted to events that were happening right now. And the Vertimill, you don't have a lot of time to react if you're reacting right when it's upset. We wanted to give them some sort of warning so they could prevent this downtime. And we want it to be about a minimum of 75% accurate. Because you can run these conventional analytics and you can see a lot of different alarms, and you test them and they don't cut it. And so we wanted to make sure it was at least 75% accurate so they would depend on it when they needed to. We identified the 10 data streams or patterns that would potentially give us good reading on when bad ore was coming. The problem with these patterns is the magnitude and the frequency and the consistency wasn't there. So our conventional analytics method, we couldn't produce a good, technically an effective or reliable warning. And that's when we realized we needed to find a different approach. So that was months and months of staring at trends and running any sort of analytic we could think. So fortunately for us, we met Crick Waters, who invited me down here today to terrify me on stage, and at an OSI-SOF event in Salt Lake City. And he introduced us to falconry. And falconry was really cool. It's actually, it's a software for the SME, the subject matter expert. And it will take similar operation signals and combine them. So for instance, you can plug a bunch of data streams into this software, and it has embedded statistical analytics, and it'll find those similar operation conditions, and then it puts them in this really nice identifiable graphical format. So I can go out and tell people what colors of the rainbow I'm seeing today and ask them, well, what's happening? What are you doing? And that makes it very easy for me. So, but once you have these colors or this graphical format, you can then add context to them. And that's where the learning part comes in. And that's the most exciting part. So we decided to give it a try. As Scott mentioned, we were on we did these 2 bets, and one of the bets we were actually teaching people the process, which can be, it's not as simple as that slide I showed you that got to the punchline quicker than I did. It's going through the process and explaining the ins and outs and the feelings and the vibrations. It is time consuming and torturous sometimes. So we took on this, we tried to run the software for this SME, and in about 2 months, we had insight to things that we didn't even know about. We had deployment back to our DCS, and we also found some things we didn't realize were happening, or we realized, but we hadn't proven them out yet. So like I said, the SME can add the context. So what that means is they will take a period of time and they will just essentially add a fact to that period of time. The way we added facts is we just went through history, went through our logs, went through data that we recognized. And we were able to go in here and grab just time-based facts. And essentially, so we added the good, the bad, and the ugly to the Vertimill operations. The good meaning good ore grade or good running conditions, bad meaning bad ore grade. And ugly was an indication that the Vertimill was unhealthy, say there was not enough balls in it or it was overloaded or something like that. So after you add all these facts, Falconry will then let you build a model. So you have this model that you can run history on. You can test its accuracy by going back as far as you have historical data. After you validate your model, you can then turn it on real time. And that's actually what we're doing today. Our model is currently living. We are always improving it. I'm out there with the control operators and operations every day to figure out why the model changed colors, and I will go in and add facts, and then they're receiving the feedback. So we haven't built that loop in yet. It's in process to take the history and build it back into the model, which we're very excited about. But right now it's communication, and that's how we're teaching our model. One thing we did notice when we were building this model is it would have been super convenient for us to just plug all 10 signals in and everything came out just dandy and we had the answer. That's why it's really great for the SME to work on this software, because with the subject matter expert, we were able to break down the problem a little bit easier because it was actually pretty complex. Because there's an offset in our process. There's a 2-hour time period from the ore comes in to when it goes and turns into that paste in the Vertimill or gets ground down in the Vertimill. So we decided to actually break up this problem by the type of material that we were processing at the time, or by the type of operation we were running. And that came about, we broke it up into the 3 sections. So we broke it up into a dry section, which is calcining, heating up the ore. Broke it up into a wet section, which was our dissolving section, where we're actually pulling out as much product as we can. And then our grinding section, where we're trying to break up the insolubles. And we discovered something really fantastic. We honestly expected, in our heads, we thought ore goes in bad and Vertimill 2 hours later, it's mad at us, correct? Well, we were wrong in some cases. In some other cases, we saw some other interesting behaviors where it happened very fast. But one of the patterns we pulled presented this cascade. So we were able to do a 3-stage alarm. So we were able to see, in this picture here, the blue means bad. Blue is bad condition of some sort that we've identified. So in the first section, we're almost 12 hours in advance of the Vertimill actually shutting down, which on the very right hand of the screen is this gap in the original drying section. And then you can see it starts banding and building up as it saturates that second stage, the second alarm. And finally, we get to the Vertimill where it saturates and builds up there. We did not expect this saturation. So we were really surprised and excited that now we could give our operators an indication how to run the unit. We can, instead of just cutting back because they think they're gonna fail, they can not cut back so much. It's not affecting the Vertimill yet. You know, we can maximize how we run this unit. Let's see. I believe we're back up to Scott. He's going to discuss our operation. Yeah, that right there.
Thank you, Jolene.
No problem.
Am I back on? So we went through figuring out this pattern. Now we've got this data in a pie system. But talking to the surface manager, that's not good enough. He sees value here, but until I can get it back into the operator's hands, there's not value. Value, potential, not value. So let me talk for a minute about our operators. Our operators are tremendously smart. Many of them have run this plant for 20, 30, 40 years, have a ton of expertise up here. Some of them can walk out on the plant floor and by sound, pick up something. It's kind of like a a mother in a large crowded room, she can hear her baby crying over in the corner, right? By sound, they can detect something's wrong with this plant, I need to go make a change. So, but the interesting thing is when we bring those operators together and they bring their expertise, not that expertise doesn't always agree. This person has, hey, when I see this condition, I run it this way. The next person has a different opinion on how to run it. So what we are trying to do, number one, is take that expertise out of their head and give them some information that they can make better informed decisions on, standardize those decisions, and so with the expertise and with data, get to a better, more consistent result. So back to the problem. So we have our 3-stage alarm. The first warning up here of insol saturation, second warning, third warning. So we work with our partners OSI Soft to figure out, I've got this data in Pi, I've got a trigger, how do I get that information back into my DCS so my operators watching the process can know about it right away and can take action. So we're feeding that back into, and we just solved this challenge last month, and so there's an alarm back on the DCS screen, right there in their flow, in their standard flow, I've got an alarm. Vertimill overload, ball charge, bad ore, something's going on. They can then, we connected the dots, so when they see that, there's a code, 7001. They can come over to a different screen, type in that code, find their core site dashboard, and this is Unit 7 Health, and now they can drill in and learn more information, validate that the alarm is valid, and decide what action to take. In addition, through this process, through this learning, we mentioned before about our ore grade. And when that goes to the lab, it's the next day we hear about it. Well, with our engineers, as they started thinking about this, they're like, we know the CO2 that goes into our calciner, we know the CO2 that comes out of it. Based on that, we know what 100% trona should produce, and we know how much gas we're feeding into it. We ought to be able to calculate the ore grade, and so within a matter of weeks, we were presenting this chart. Now we're still validating how accurate that is compared to the lab, but we already have seen that directionally it's right. You start seeing the ore grade go up, that's a good sign. You start seeing the ore grade go down, it's a warning sign. So that's important. We also started looking at our calculated ore rate in terms of the flow rate through the system. One of the great things about this experiment has been the collaboration. And so we had an event early, an upset condition early in January. We were all together in a room a couple days later. We were looking at history of the data. We were able to pull this information up. Somebody in the room says, what about these two factors? Draw those onto the screen and see that in that time span. And we came to a decision that particular day with that type of fault, the flow rate maxed. It exceeded the total benchmark capacity of this particular unit. So our DCS admin was there. I can put a limiter on that, and we've not seen that issue again. We solved that one issue. So the collaboration of being able to bring this data in, make real-time decisions with the operators, and get to a better result. So this is how we're operationalizing. We're working through the process of making sure all the operators are trained, making sure they know what the alarms mean, what decisions to take, fine-tuning the alarm, as Jolene mentioned. So we expect that to continue this quarter, but then we expect that this alarm will be running on its own. We're looking for how can we make that learning in the model more automated and less people-intensive as we get closer and closer to perfection. And then we're already starting to backlog and prioritize what are the next processes that we want to analyze, what are the next machinery that we want to look at in terms of predictive maintenance. And basically build a factory of how do we roll these in, how do we set these alarms, and how would you go forward. One other challenge we have is these DCS alarms, our control room operator, 3 or 4 operators, they get 4,000 to 5,000 alarms in a week. So ton of nuisance alarms, 80 to 90% of those are not value. They're single point pressure, single point temperature, not value in itself. So we've agreed with operations that we're going to do our alarm and our analytics in Pi. We're going to pass those triggers back in. Then they can come and get more contextual information about that alarm. But there's a process of how do we eliminate those nuisance alarms and get those out of the way, because today there could be a valid alarm and it's ignored because it's a needle in the haystack. Go forward. move the slide forward. There we go. Benefits. From an operations perspective, we've talked about this. Give the operators alarm visibility in their system and their DCS screens they're looking at today. So this person's looking at unit 4, he can be seeing his screen. This person's looking at a different part of the process, he can be looking at his alarms. And give them confidence to make the right decisions regarding the optimal flow rate. So before this alarm, what's happening, and as I mentioned, they lost visibility to the ore grade changes. They may have waited too long, and all of a sudden we're in an upset condition when they realize it, and then we have 4 to 24 hours of downtime, right? Or they were worried about that, they ramped the flow rate down and ran it in a decayed state longer than it needed to because their shift's over in 6 hours or 12 hours. They didn't want any issues to happen while they were on, so they're going to run it at 40, 50% slower, right? By giving them this information, we can give them confidence to make the decision of bad ore coming in, cut the rate back 10%, cut the rate back 20%, watch it as those insolubles get ground up, and tell them when to hit the gas pedal again and pulling that tonnage rate up. Business benefits, that's important. I didn't mention before, but we sell at capacity. So when we have unplanned downtime, that's dollars that our cash register is not ringing. And so we want to eliminate and minimize that. And so the benefits are measurable and significant. And Jolene talked about some of the technical side. With our other bet with this decision science and heavy data scientist, one of our lessons learned was this particular company came in and they only had one other process manufacturing experience. So great data science, great machine learning, but we spent a lot of time training them on our process. With our partner Falconry, we could put our operator, our subject matter expert, they could learn the tool. They don't have to be data scientists because that data science is built into the tool, and they could figure out the patterns, and we got a result much quicker. We still may use this other model for certain cases, and we've got some lessons learned, but different models, and this one got us to a result much faster. The visual pattern recognition were easy to see, and then it reduced time, basically time to market. It was in a matter of days to weeks that we were getting valuable input. We spent the time to go back and look at historical data and see how it was producing. We could fine-tune that algorithm and then move it forward and present it. So in summary, one more slide, please. As I wrap up our journey, our lesson learned on this specific problem, we knew we had a Vertimill issue, we knew we had ore grade changes, we knew things could get into upset condition without our operators knowing. But the actual root cause, we found that there was multiple different variations. And these three-stage alarms allowing us to give visibility and information so the operator can take the right corrective action and optimize the throughput. It is iterative, so it's a learning process, us talking to the operators, us showing them what knowledge they can get from this information and passing that on. And then as we go forward, and I mentioned, so we started small, we found a few bets, but it really started with leadership and vision of where we wanted to go with the smart plant. It started with the business value that we were trying to drive. And now as we're realizing that potential, we want to operationalize it and then move forward with other alarms and other challenges and problems within the plant. So I'll turn it back over to Peter.